Processing. So my name is Donald Whyte. Just a little bit of background about myself. I'm a software engineer that works for an algorithmic trading fund. So we build automated trading strategies to try and make money. Part of my time is spent building our scalable data infrastructure, and the other part is spent building real-time trading systems. So I'm primarily a Python and C++ developer, as well as a bit of a Rust enthusiast. And what I'm going to be talking about today is Python and using Python for data processing. Now, we know that Python is a hugely popular tool for data analysis. A JetBrains survey last year actually showed that half of all use cases in businesses actually come from data analysis now, and not just web development, which was Python's primary use case before. But why? So Python is suitable for research because it's high level and easy to use. It doesn't require advanced programming knowledge, which enables researchers to iterate on ideas and develop very, very quickly. But unlike a lot of other research-oriented languages, it's suitable for production as well. It's a general purpose language that's useful outside of research and analysis. And there's a huge ecosystem of packages for supporting production deployments like logging, profiling, monitoring, etc. So Python's strength is that it's good at both. It enables researchers to build stuff, to iterate on ideas quickly, but also it enables developers to deploy those ideas to production as well. And so we want to use the same code for prod and research, so Python is a good fit for this. But pure Python is slow. It's not well known that Python is not very fast. If you compare it to any natively compiled programming language, just using pure Python routines is typically pretty slow. Here's some basic benchmarks on how much faster C is, for example, when you just build a naive implementation of certain algorithms in C. So, which makes it actually bad for research if you use pure Python, because if you're doing lots of heavy data processing, you have these very slow experimentation cycles. And it's also bad for production, because you can't run time-sensitive data processing or computational tasks. So the solution is Python's data processing ecosystem. There are a wealth of packages in Python for analyzing data conveniently and fast. What we're going to focus on today is NumPy. So NumPy is essentially the heart of scientific computing in Python. It stores and operates on data in C code and C structures, and that's what makes it avoid the slowness of Python. So this is the foundation. NumPy is the foundation of many, many scientific packages I'm sure many of you have used before. So our focus on this talk is to show how to use NumPy to process numerical data, exploring how we can use it along with vectorization to dramatically boost performance of data processing tasks, but also keeping the productivity that Python gives us. So we're still keeping that high level, easy to use language there. So the outline is we're going to build an algorithmic trading strategy using stock price data. We're going to process that stock price data in pure Python, but then we're going to optimize and speed up our processing using NumPy and vectorization, and then also using another tool called Number. And the final optimized solution is almost 2,000 times faster than just using pure Python alone. So let's do it. Let's make some cash. So suppose we're a programmer and we're tired of the grind, we're tired of working for a company. We decide that, you know, we can make an algorithmic trading strategy that is going to make us millions. Sounds great. Turns out there's a lot of data available online to support this. So there's an online data set where you can get the prices of over 7,000 US stocks historically. And essentially these are a collection of CSV files. So we have 7,000 CSV files, one file per stock, and each CSV file contains two columns: the date and the price of that particular stock at the market close on that date. So as you can see here for Apple, we have from 1984 until 2017. And you know, if we plot this, we get something like this. Not entirely a surprise, because stock prices have generally increased as time's gone on. So the data set's actually quite small. It's only a gigabyte in size, but we're going to be doing a lot of heavy processing on it, and so this is what's going to take a lot of time. Our goal is to build a program that generates a list of trades to make with one trade list a day. So we're going to write a bot that submits one set of trades, buy or sells of stocks, every single day. Disclaimer, this strategy that I'm about to do is for demonstration purposes only. Please don't implement this at home. You will not make money. But even though this strategy is a bit of a naive toy strategy, its actual high-level structure does reflect what many real-world automated trading strategies do. So this overall approach is actually used in real life by people to make money. So how are we going to generate these trade lists? So we're going to leverage two fundamental behaviors about stock prices, or believed fundamental behaviors. The first is that prices revert to the mean. So you imagine any kind of time series, prices in this case, and price changes over time. Now, it may trend upwards or downwards, but it generally bounces around this kind of moving average. So what we're going to do is we're going to calculate the stock's daily return. So this is the changes in stock price. And what we expect to see is it hovering around 0, because generally, even though prices bounce, generally they kind of revert back to this like moving average. And we can calculate daily returns by taking the price today and subtracting it, the price from yesterday. So essentially, we're just calculating the change in price every single day. And we end up with something like this. So for 2 weeks in 2016, for Apple, the Apple stock, we get something like this. So you see that the return, which is the change in price, is kind of bouncing around 0, which is expected because if prices revert to the mean, we always expect if a price goes down, it will eventually go back up to go back to the mean. So we get this kind of like down and up structure. And our mean reversion trading strategy, which is what this type of strategy is called, what we do is we buy or sell a stock when this change exceeds a threshold. So suppose if we have $90,000 to trade with. If we take this example, these 2 weeks of Apple stock price changes, when the change in price exceeds a certain threshold, we're gonna buy. So for example here, the price dips, it changes more than $1, so it's reduced by $2 from the previous day. So we buy it, then we hold it for 1 day, and then immediately the day after, we sell it. So sounds simple, right? But if you believe in mean reversion, then if a price goes down, it must eventually come back up to match the average. So we actually make money because we've bought low and we've sold high. And we repeat this process again and again when we exceed thresholds. Sometimes we lose money, and sometimes we gain money. And the whole point of this strategy is that you're going to gain money in these trade pairs more than you will lose money. In this particular example, we got a 2% return on investment, which isn't bad. But yeah, the goal is we want to make more of these right trades where things are reverting back to the average than wrong trades. But it's a problem. What if the price doesn't revert to the mean? So often stock prices have something called momentum. So you can imagine, say, Apple has some sort of announcement that shows that they've doubled their sales, their iPhone sales. That's going to cause stock traders to invest very heavily in Apple. And so the price isn't going to revert back to the mean. It's just going to keep going up and up and up. And in fact, the speed of that price increase actually accelerates. So it gets faster as time goes on. If we try and use mean reversion, so we buy and then sell the next day, we're going to keep losing money because the price is increasing, and we buy and then we sell, and then we buy again, and so on. And so we're actually buying low and we're selling high, but then because we keep doing that, we could just buy it once and then sell it right at the end, and we would avoid trading costs and things like that. So mean reversion strategy often loses money when stocks go through this type of momentum phase, when they're accelerating in price, when they're increasing in price at accelerating rates or decreasing at accelerating rates. So we leverage another fundamental behavior about stocks, which is that they're correlated. So Apple, for example, and Amazon move together. So when Amazon increases or decreases in price, so does Apple more often than not, as you can see from this time series. You see here that when Apple, the blue line, increases, so does Amazon, which is the orange line. But also, Apple actually correlates with the whole US stock market. So if you take like the average return of the whole US stock market, it actually correlates with Apple. So when the whole stock market goes down, Apple goes down, which again isn't entirely surprising. But we can leverage these behaviors to avoid trading using this mean reversion strategy when by considering these stock correlations. So we only use mean reversion when stocks are hovering around this same price. So they go down, and then they go up again the next day, and they go down, and so on. We don't use mean reversion if the stocks keep accelerating, and we're going to try and use correlations to detect if a stock is increasing highly or decreasing at increasing speeds. So I don't really have the time to go into the detail on exactly how this works. It's quite numerically complicated, and there's a lot of calculations involved. But essentially what we do is we take these stock returns, so these changes in prices for every single stock, for all 7,000 of our stocks. We combine it somehow with the correlation that that stock has with all the other stocks, and then we have this unexplained stock returns. So we take the returns, we combine it with the correlations, and we have this new time series. And these unexplained stock returns represent the change in price that we can't explain by the stock market. So if the stock market overall is going up, then if Apple goes up, we don't want to apply mean reversion because the whole market's gone up and it's probably not going to come back down. Whereas if only Apple has increased and the rest of the stock market hasn't, then there's a high chance that that price increase is just noise. It doesn't represent a fundamental change in price that will stay forever, and therefore it will come back down to the mean. Yeah, so essentially these unexplained returns represent the movements in stock prices we can't explain. However, this is a really difficult step and it's quite computationally heavy. Two methods for taking this change in prices time series, this returns time series, and then adjusting it such that we only have the unexplained returns. Often these two techniques are used, principal components analysis and linear regression. Again, I don't have the time in this talk to go into the detail on exactly how they're used. Feel free to ask questions after the talk. But just know that these are used in this strategy, and these are fairly numerically heavy. So let's actually try our trading strategy that leverages these two fundamental behaviors. So what we're going to do is every weekday, just before the US stock market closes, we're going to calculate all the 7,000 stocks' daily returns for the past year, calculate the correlation between each stock's returns, use the correlations and the previous returns combined to get this unexplained stock returns, the noise, the price noise, change noises that we expect will revert back to the mean, and then we buy and sell decided stocks by applying this mean reversion concept. We wait until tomorrow, and then we get rid of the stocks that we bought and borrowed. So we only ever hold on to a stock for one day. We buy it and then immediately sell it the next day, assuming that the price is going to bounce back to the mean. Yeah. So we're going to simulate how much money we would make historically by using this pricing data. So we can simulate how well the strategy would do in the past to see if it would be very useful in the future. We're going to simulate from 1990 until 2017, which is actually where this pricing data ends. And we're going to initially write the strategy in pure Python. We run the simulation, and the result initially looks pretty good. So if we look at the early years in this simulation, we actually make a lot of money. So every year there's about 3 or 4% returns that are made, which seems great. So our overall cumulative returns look pretty good. But in reality, it stops making money. And so as time goes on, as we get into the early 2000s, we actually start losing money and don't really make any money anymore. And the reason is because often, basically, no one was doing these types of automated trading strategies in the 90s, whereas everyone started doing them in the 2000s. And so all of a sudden, the competition is a lot harder, and these types of algorithms aren't actually that efficient in their simple form. So you have to work a lot harder and calculate these unexplained stock returns in more and more complex ways than you used to be able to do. So as we can see from these yearly returns, again, it was making money. The return every year was above 0%, and then eventually in 2001, it starts getting quite bad. We occasionally make money, but for the most part, we lose money. So our first attempt has failed, which is not surprising. This stuff is hard. If it was easy, everyone would be doing it. But the issue is that if I was to actually run this full simulation, it would take, in pure Python, it would take 3 years. There's a lot of computation in that decision step with the principal components analysis and linear regression. And these long simulations, I mean, obviously this is a bit of a huge time, but even if it takes a day or 2 days, it's often a bit of an issue. You want to be able to change and tune your strategies constantly to try and find out what works best. You want to have this run in hours, not years. So what went wrong? Well, 3 steps are computationally heavy. These 3 steps are returns, where you calculate each stock's daily returns, correlation, where you calculate the correlation between each stock, and then this decision step, which is a step which uses principal components analysis and linear regression. But how much computation is exactly required? So yesterday, I went through each formula to calculate all these 3 steps. And for the full simulation, I found that it actually took 2 trillion operations in total. So you can see here, for example, that the correlation step takes 72 trillion operations. And by operation, I'm defining this as like an addition, a subtraction, divide, etc. Those types of operations. So in total, to do the full simulation, it's around 200 trillion operations. And this is for a very simple strategy, which is a lot. So if we actually break this down in pure Python, we see that the return step is very quick. It's only half a day, well, relatively quick. And then the rest are years, which is obviously not acceptable. And I think everyone kind of knows why Python is slow, so I'm not going to dwell on the details. But essentially, the 3 primary reasons is that first one is that Python uses dynamic typing, which means that every single time you're performing any kind of numerical operation, there's typecasting checks that need to be done, which is just making all the operations several times slower immediately. It's interpreted, not compiled, so the compiler can't do any advanced optimization on the code. And also, the big one is fragmented memory access. Any list in Python is actually implemented as a list of pointers that point to the heap. And so suddenly, if you're iterating for a list of numbers to do some calculations, you're thrashing the CPU cache because you're retrieving from various different parts of memory. So how can we do better? This is where we enter with NumPy. So NumPy, as I mentioned, is the fundamental high-performance computing package in Python. Lots of libraries and frameworks are built on it. Essentially, all NumPy is it provides this multi-dimensional array class, and it stores all that data that's stored in that array in C for efficiency. And it has routines for very fast operations on these arrays. So to give you an example of this particular array type, so this array is called numpy.ndArray. If we were to just use NumPy to create an array of 9 numbers from 0 to 8, 9 floating point numbers, what it actually looks like in memory is this. So all the NumPy array is a pointer to a data buffer. So you have this contiguous block of 9 8-byte slots because there's 9 floats. And what's quite interesting is when you store your data in this structure, in this flat memory block, you can actually do some quite powerful operations at no cost. So you see there's this shape and strides attributes. So shape represents the dimensions of the array. Arrays are fixed size in NumPy. And strides tells NumPy how many bytes in the memory block to move to get to the next element. So here we have 64-bit floats. So the strides is 8. When you move 8 bytes in the buffer to move to the next element. And this is quite interesting because it enables you to do some very interesting things. For example, we can take this 9-sized flat 1D array and reshape it into a 3x3 matrix, and with 0 copies involved, by just simply changing the shapes and strides. So the memory buffer is exactly the same, but the shape and strides have changed. So you see now the shape is 3.3 and strides is 24.8, which says move 24 bytes to move to the next row, but move 8 bytes to move to the next column. And again, the data has not changed at all. And we can do things like we can remove 1 column from the matrix. So we could use Python slicing notation, which again changes the shape attribute and changes the array to a 3x2 matrix. And the key here is that reshaping or slicing creates a view. No copies are made. And this enables us to do a lot of computation with very little cost. So the performance benefits are essentially that the data is stored contiguously. There's no memory overhead. You have cache locality, which you don't have with Python lists. There are no copies for common reshaping or slicing operations, and there's very fast logical mathematical operations that you can apply on these arrays. Just a basic benchmark, if we were to add 2 arrays of 10 million numbers, in pure Python, it might look like this. Assume that sum doesn't exist for this particular example. I want to keep this simple. What you would do is you would have 2 lists with 10 million numbers, and you could use a list comprehension to add them. In NumPy, there are many ways you can do this. You could create 2 NumPy arrays, create an empty output array, and then loop through each NumPy array. Or you can just use the built-in NumPy operator. And when we time these on this laptop, well, on my personal laptop, what we get is that Python takes 1 second to do the list comprehension. NumPy with loops take 3.4 seconds, so actually longer. But the built-in NumPy routine is 0.03 seconds. So we get a 36 times speed up just by using NumPy to add these numbers. What's interesting and an important point is that NumPy with loops takes a lot longer. It's 4 times longer, almost 4 times longer, to iterate through a NumPy array than it is to do a list comprehension in Python. And this is very important to understand because when you explicitly loop over a NumPy array, you're actually creating even more inefficiencies than just using Python alone. What's actually happening, it's a bit of a complex diagram, but what's happening is that every iteration, you're moving from the Python level to the NumPy C level. So every single loop iteration for every number, you're going into the C level, you're taking 2 numbers, bringing them into the Python layer, and then adding them. And so the bringing it into the Python layer copies the numbers, you add them, and then you send them back into the NumPy layer to get set into this output array. And this is very, very, very slow and inefficient. What you should always do when using NumPy is you want to keep the computation in C. You always push it down to the C level and do no explicit looping in Python. So by using the built-in addition operator, all the code is actually run in the C level, and so we can get the advantage of all of these optimizations that C can do that Python can't. And so yeah, the key is you don't loop through these types of arrays. You always avoid explicit looping, and you always utilize Python's built-in operators. So there's another problem with using or seeming problem when using NumPy, and that is when you want to apply single scalars to a whole array. So for example, suppose you want to add 1 to an array. Now, it might seem like to use NumPy's built-in addition operator, you would have to create an array of the same size as your target array of all 1s and then add them. But in reality, it doesn't actually work like that. What you can do instead is you can broadcast smaller values to the whole array without copying. So you can actually, with NumPy, use the built-in operators to just apply a scalar value like 1, 5, 10, whatever, and you can add it or multiply a whole array or matrix of numbers without any copying. What actually happens is the 1 is broadcast to the output array. And again, you can even do this with vector matrix multiplication, for example, which again will create massive speed up because there's no copying involved, but you're also still using the NumPy layer. And when we use NumPy for our trading simulation, as a recap, these are the 3 steps: returns, correlation, and decision. Let's show how we would change the first step to use NumPy. So this is the simplest step, which is why I'm explaining this particular one. But the return step, to recap, is where you calculate each stock's daily returns for the past year. And again, a return, we're going to be considering this as a percentage. So percentage return, or change from the previous day, is just today's price minus yesterday's price over yesterday's price. And this will give us a number like 2% to indicate that the price has changed by 2% from yesterday. Now, as a concrete example, if we were to calculate Apple's returns on the 2nd of August 2017, we just take its price, subtract it by yesterday's price, divide it by yesterday's price, and then we get this percentage return. But we need to do this for all stocks on all days. So we have essentially a quadratic problem where we have days times stocks to sell values to calculate. Now we could use a for loop, but as we know, that's slow. It's inefficient. Lots of copies and slow operations are being run in Python code. So instead, we use NumPy in the correct way by packing all the stock prices for all dates into a 2-dimensional matrix, and then we perform bulk operations on this matrix. We just transform in this matrix to keep the computation in C. So it might look something like this, where on the columns you have the stocks, and then on the rows you have the dates. And the returns matrix that we want to calculate, or the output that we want, is we want to take these prices and we want to change it to be the percentage change on each day. And just to give you an example, that particular cell from the returns matrix is computed from those 2 cells of the price matrix. But But instead of calculating all these cells one by one using Python loops, we're going to use these bulk operations. So all we need to do is take our price matrix. So we munge the data into this matrix form. We do a shift in NumPy to basically offset the prices by 1. So you see here, Apple's price on the 11th, on the 8th of November is 45, but then we just shift it down 1. We take that returns formula I showed earlier, and we just substitute each part of the formula with the matrix, with the matrices. So it just looks like this. Today's price minus yesterday's price is the today's price matrix minus yesterday's price matrix, and it all just works magically, and that gives us our returns matrix that we want. And the NumPy code for this is very simple. So we just create a Python price matrix. So we've created this two-dimensional matrix in NumPy, which is shaped by the number of dates in the simulation times by the number of stocks that we want to trade. We populate it by loading those CSV files from earlier into the matrix. We then calculate this yesterday's pricing matrix, and it only takes 2 lines of code. And then we calculate the returns like that. So instead of doing any explicit for looping, we've essentially gotten rid of the loops and packed all the data in these NumPy structures, which avoids the Python inefficiencies. And when we compare the times, they're quite profound. So the total time for every single day to calculate returns has gone from 642 minutes to 8 minutes. So we get a 79 times speed up just by doing this. Now, returns is the simplest step, and actually the cheapest. When we do similar optimizations for the correlation and decision steps, the 2 other steps, we actually get this. So we go from 3 years to 2.8 days. So the actual speed up is 395 times just by expressing things in NumPy arrays and performing bulk operations on them. And NumPy is so much faster, again, to recap, because there's no extra memory overhead and there's minimal copying, and all these operations are executed in the compiled code. There's no hot looping in Python. A big other reason is vectorization. Now, vectorization is defined as the process of converting an algorithm from operating on a single value to operating on a set of values at a time. Basically, what this means is modern CPUs, they run a single instruction on multiple data points at the same time. To give you a concrete example, if again we go back to the example of adding a bunch of ones to an array, it might seem like that adding these ones would take n instructions. So if the array was sized n, then we need n addition instructions because we have n numbers to add 1 to. But in reality, if you express your data in this contiguous memory block, what a lot of CPUs do is they apply the same instruction to multiple elements at a time. And so what you get is that the CPU will load in 4 numbers and apply 1 addition instruction each time. One thing I want to make quite clear is that people use vectorized and vectorization in different ways. So when you're referring to native code and when you're referring to just CPUs or hardware, vectorization is specifically about applying single operations to multiple data items at a time. So essentially what I just described, where we're running multiple the same instruction for multiple data points. But in Python, people tend to use vectorization just to basically mean expressing your problem in vector matrix form and keeping that computation in some C level using NumPy or some other library. Again, both involve making algorithms make algorithms express the problem in vector matrix form. So you avoid this hot looping essentially. And for vectorization for the trading simulation, we already got this for free because we were using native NumPy operations, and this vectorizes the code already. But not always. So you often need to rewrite your algorithm to make it vectorize, and often that is actually quite tricky. It's not always trivial to have a vectorized algorithm. But also not all algorithms are vectorizable. There are times where you cannot express things in simple vector matrix maths. As we see here, this is the timings from using NumPy. We see that the decision step is still taking 2.6 days. So we may have gone from 3 years to 3 days, but we still have this like a huge amount of inefficiency in this third step because some of it is difficult or impossible to vectorize. So this leads on to the next point. So there's a tool called Number, which solves this problem. So again, our problem is that not all algorithms are vectorizable, But what we do to solve that is we compile that non-vectorizable Python code to native machine instructions. So we use number to annotate Python functions with decorators, and then that compiles this Python code to native machine instructions using LLVM. So the decorator is number.jit, and to give you an example, suppose we are summing an array of numbers. So we have a simple array, we're trying to add to it, and we get this. Now, we can sprinkle some number magic on it. So this is a pure Python code. If all we do is say from number import jit, and then at jit no Python equals true, the no Python part tells it must compile to optimize machine code. We get this. So it goes from 1.7 seconds to sum up this large array of numbers to 0.0065. So we get 270 times speed up just by adding this decorator. One thing to note is that number automatically deduces the type of your functions. So here, what it would actually do is when you call the function and pass it some value, then it will infer the type and compile code, native machine code, to handle that type. Because compiled code needs to know the types in advance. What you can do instead, though, is you can actually manually specify the type. And that can often speed up processing even further. Sometimes NumPy's type inference isn't the best. So if you explicitly specify the types, and what this is saying is, at jit this function and force it to return an integer and force it to take an array of integers. And by doing that, you can actually make it faster. Now, number might seem like magic, 270 times speed up just by adding one decorator, but in reality, it can be very limited. You have a restricted number of language features when you have no Python equals true. So you can't just use arbitrary Python classes or most Python features when you JIT functions, because they're relying on compiling it to native machine code, which doesn't have the same flexibility as Python. And also, some people might argue it makes the code a bit more verbose if you have to annotate with types. I like type annotations, so I don't mind that, but some people don't like the fact that you have to have @jit and then specify the types on every function. So when we do this to the trading simulation, we add to all of our numerical computation functions @jit no Python equals true, we get this. So the returns and correlation steps don't change. They're the same time as before because they were already using NumPy and heavily optimized instructions. But because there was this looping in this non-vectorizable portion of the decision code, we get massive speed up when we use @jit on those non-vectorizable components of the algorithm. And so we go from 2.6 days to 0.37 days. And so now we've gone to running this full simulation in half a day. And that's pretty impressive on a single MacBook Pro. 200 trillion floating point operations basically in about 0.6 days, so like 13 hours or something like that. So overall, when using both NumPy and number in conjunction, we've both vectorized all the code we can, and then for everything we can't vectorize, we have compiled it to native machine code instructions using number. Now, the final timings, to summarize, is pure Python, it took 3 years. In NumPy, we got it down dramatically, but there was still some inefficiencies, and so we used number to cover the rest of those inefficiencies, and now we're down to 0.5 days. So 3 years to 14 hours, essentially, on a single MacBook Pro as well. So that's pretty much the talk. To summarize, Python is great for research, but out of the box, Python's slow. There's increasing demands for faster and real-time data processing. You want to process large volumes of data, or in this case, small volumes of data, but do really heavy numerical operations on them. And standard Python is not viable for these use cases, because it's bad for the slowness makes it bad for research and bad for production, running time-sensitive computational models in production. So we can still use Python for research and production, because we can utilize Python's larger ecosystem of scientific computing packages. And we do this by keeping all the computation in native code where possible, vectorizing using NumPy, and for whatever we can't, we use number or a similar tool to optimize. Now, if this isn't enough, you can actually also parallelize. So often a very common step when people are doing heavy computation is to run parts of the computation on different boxes. But I would urge people to not throw the problem to DevOps. What I see a lot of people do is their code is slow, so they decide to just parallelize the problem, run it on, say, 50 machines on some machine cluster, but you're actually just, moving the problem somewhere else. Yes, sometimes it might be a little bit tough to optimize code, but it's also tough managing a machine cluster, handling like machine failures, things like that, recovering from that. There's a host of other problems when you begin to parallelize on compute clusters. So just using Number and NumPy and tools like it alone can yield thousands of times the speed up. So it's definitely worth trying that first before necessarily moving to the sort of heavyweight solution of parallelizing. And that's it. Spasiba.
First of all, thanks for the talk. I have one question.
Yep.
How many money you earn while doing this speech?
0.
What a pity.
Thank you. Donald, could you please repeat the JIT part? What exactly does the JIT decorator do?
Sorry?
Could you please repeat the JIT part of your speech? The JIT decorator.
Oh, yeah, sure. So essentially, what you can do, if you have just regular Python functions, you can annotate them with this JIT decorator, and that will tell this library called number to take the Python instructions in like Python code and compile it into machine level instructions. So it uses LLVM, if you're familiar with LLVM. It's basically a tool for it's like an intermediate thing for compiling stuff to native code. So, for example, basically what this does is it makes it as if you were writing this function in C. So C, of course, is very fast. It's very close to the machine. It's low level. And what JIT does is it does the same thing. So number just takes the Python code and has logic and features that just take it and then compile it to native machine instructions, CPU instructions for you. But it is quite limited. So, of course, it's not magic, right? So, if you were to use loads of heavy Python dynamic features, it wouldn't work because you wouldn't be able to compile that to native code. So, basically, you would use something like number to take the heavy for loops, essentially. Whenever you've got a loop which is doing lots of computation, you take that and you @JIT it, and then you compile it to native machine instructions, and then everything else, all your boilerplate, like loading files, talking to a service, logging, whatever else, all that stuff you keep in Python because it's convenient, it's easy. But for the heavy compute portions, you do this. So this is basically the same as also, if you were, how, I don't know if you're familiar with how some Python libraries, even the Python standard library, it will, a lot of the functions are actually implemented in C, and then when you call something like the sum function in Python, it actually calls the C code. It's basically the same thing, but you don't have to write in C. You write it in Python.
Sweet.
First of all, thanks for the speech. It was great and interesting. I have two questions. First of all, what about NumPy calculation? How we can get the more performance of NumPy on hardware? Maybe we need to use a lot more threads in CPU, some tips about this. And second question, it is about you use NumPy for matrix separation. Why choose NumPy? For example, you can choose some special matrix libraries in frameworks like TensorFlow, Tiana, and they can work not only CPU and special hardware, GPU, TPU. Why you choose NumPy?
So the reason for choosing NumPy for this specific talk is really that it's simple. So the main reason for using NumPy is that it's like very fast and efficient, but it's also very simple to explain. So the main point of the talk is primarily that anything that's computationally heavy, you use tools NumPy or Theano or TensorFlow to push it down to the machine code level, essentially. So using NumPy here was really just more for simplicity. In reality, for this specific problem, I would probably use Pandas because Pandas is a tool which is slightly higher level than NumPy, but adds lots of useful features, particularly in dealing with time series data. Now, using NumPy efficiently and these other tools like TensorFlow. So you're right in that generally NumPy is really driven to be used on CPUs, not GPUs. That's definitely true. And so if you want really heavily vectorized and performant code, yes, you can use something like Theano. NumPy, though, is a lot closer to how you would express problems in Python natively. So TensorFlow and Theano, you're expressing the problem in a very different way, and a lot of people are not necessarily familiar with doing it that way. So for the purposes of helping out your teammates and keeping the code base understandable, if you don't need to go to the far extreme of optimizing, like running stuff on GPUs, if you don't have that requirement, I would still opt to use something like NumPy, because even though technically it's harder to run on GPUs and things like that, I would still use NumPy because it's a lot closer to how Python and programming languages generally work, so it's a lot easier for people to understand. But yes, I would say one of the comment about optimizing NumPy is often what you can do is if you're doing operations that are embarrassingly parallel, so maybe you want to, or just somewhat easy to parallelize. For example, you can do parallel matrix multiplication in some way, in like a bit of a hacky way. If you wanted to do something like that, what you could do is you write your data to shared memory. So you can write it to a memory mapped file, which is a native Unix feature, which basically writes data to a file, but from the processor's perspective, from the program's perspective, it looks just like RAM memory. And so often what I do is I take some big data like this pricing data, you might write it to a memory mapped file, which is efficient to read and write from, unlike regular files, and I would then parallelize by using something like multiprocessing. So run parts of the task on different machines, but not do loads of copies from the main process to the child processes, because everything's been dumped to a mem-mapped file. I was actually originally in this talk, but I cut it out because it added a lot of time to the talk. But so that's one way I would recommend making stuff even faster in NumPy is, if possible, parallelize, but don't just blindly parallelize, because you have to copy a lot of data and it's kind of inefficient. So if you use something like memory map files, which NumPy has built-in support for, you literally type mp.memmap, then it just operates the same as a normal NumPy array. It's very efficient in that way. Yeah.
Hi, thank you for the speech. Is NumPy and numbers always enough for you, or do you use another tools to improve?
So mostly what I do is I try to keep things as simple as possible, and then only complicate when needed. So as mentioned, I start with NumPy and number. If they're not sufficient, what I typically do is I identify opportunities to parallelize, and then when I do that, I will typically go with this architecture of writing to a file on disk using memory map, a Unix feature, and parallelizing using multiprocessing. Now, if that's still inefficient, then I will parallelize on clusters. So if, for example, the data being operated on is too big to fit in RAM, or it's just really inefficient to read from disk, or parallelize because there's lots of copies involved, then I will parallelize using a machine cluster. So for example, put the data on Amazon S3 or some other object store, and then just spin up like 100 spot EC2 nodes and just go to town and have things run on those nodes. So that's typically what I do. I haven't personally needed to go further than that. Typically, the problems that I've dealt with, for the most part, have some parallelizable portion in, and so I can always fall back to parallelizing if it's really difficult. Yeah.
Okay, thank you.
Okay, more questions? Okay then.
Cool.
Thank you very much. And stop. You should choose the best question. We have only two, so will
Okay.
be the right thing. Is it?
Best question. Probably the question about using Theano TensorFlow.
Oh,
That
okay.
one, yeah.
Okay. So, yeah, it's you. Oh, nice one. Oops.
Thank you.
Yeah. Thank you. Thank you very much. And yeah. Oh, sure.
Question is about have you tried like Siphon or different technique like using instead of NumPy and NumPy?
Yep. So I have used Siphon. So actually, is this one? I have used Siphon, but and it's great. So we use it a fair bit because we have systems that receive market data. So we receive live pricing data and things like that for our trading strategies. And it comes in so fast, but we still want to use Python. And so we use Siphon to optimize a lot of that code, reduce copies, make it more efficient. Siphon's great. Siphon is good. Siphon, for those who don't know, Siphon is essentially a way, it's like almost a modified version of Python where you have Python code with special annotations and keywords that you then feed for a compiler, and it compiles your Python code to native code. But you can still use that compiled native code in other Python. The reason why I typically don't start with Siphon or don't use it for lots of things is because it's quite heavyweight in that, one, rather than just like a few functions you're adding @jit to, for example, you're having to actually, essentially you're using a different language. You're using Siphon, not Python. So you're changing the language for specific modules and things like that. So your dependency on Siphon for optimizing is greater. So it's harder to move away from Siphon if you want to do something else. Whereas something like number, again, it's just a single decorator. It's trivial to change if need be. And the second one is it kind of slightly, very slightly, but it does complicate your build process, because rather than just running Python files, suddenly you have to do this compilation step. So it just adds slight complication. But yes, I think there are situations where I would use Siphon, and those are when the efficiency of pretty much everything in your Python program, and when everything in your Python program needs to be fast. So if you have a really high load data flow, so you're receiving gigabytes of data every minute or something like that, then I would use Siphon, because every single copy matters. Everything, the whole flow needs to be optimized in C. At which point I would probably just write it in C or C++. But yeah, when you have this requirement that everything from end to end needs to be extremely fast, and you have this type of how to describe it, stream of data, then I would typically use something like Siphon, because you're basically going to have to optimize every piece of code. Whereas if it's just a case like this, where there's lots of other stuff around it, like loading files from CSV, loading stuff from CSV files, or sending something to a service, or reading data from S3, there's lots of IO-bound stuff and others boilerplate that isn't necessary to be in Python. And so, because it's only such a small subset of the actual code base needed to be heavily optimized, I just decided to use Number and NumPy, because it's lower touch, easier to deploy, and so on.
Thank you.
Cool.
So